I've been researching neural networks since completing my PhD in artificial intelligence at the University of Edinburgh in 1978. In my documented career spanning nearly 5 decades in artificial intelligence, I've witnessed the transformation of neural networks from an academic curiosity that my professors discouraged me from pursuing into the most powerful technology reshaping human civilization. The algorithms I published are now powering today's AI systems that billions of people interact with daily. When viewers hear from me today, they're learning from the scientists whose documented work created the mathematical foundations of modern neural networks. My published research began when artificial intelligence was dominated by symbolic reasoning and expert systems. While my colleagues built rule-based programs, I was fascinated by creating machines that could learn the way biological brains do. This led me to develop what became known as connections approaches to artificial intelligence. My early work focused on understanding how networks of simple processing units could exhibit complex, intelligent behavior through learning rather than explicit programming. I published the backpropagation algorithm in 1986 alongside David Remmelhart and Ronald Williams in our seminal Nature paper titled Learning Representations by Backpropagating Errors. This paper has been cited over 46,000 times and established a mathematical foundation for training multi-layered neural networks. The algorithm works by calculating prediction errors and systematically adjusting connection weights between artificial neurons to minimize those errors. What we demonstrated in that paper was revolutionary networks could learn internal representations of data that weren't explicitly programmed by humans. My research team at the University of Toronto developed the techniques that triggered the modern deep learning revolution. In the 2000s, when neural networks had fallen out of favor during what researchers called the AI winter, my lab continued pushing forward. We developed new training methods, explored different network architectures, and demonstrated that deeper networks could learn increasingly sophisticated representations of data. This persistence paid off dramatically in 2012, when my student Alex Kryszowski and I developed AlexNet. My documented work training AlexNet marked the beginning of the current AI boom. Our convolutional neural network achieved unprecedented performance on the ImageNet Visual Recognition Challenge, reducing error rates by over 40% compared to previous methods. This breakthrough demonstrated that deep neural networks, when trained on sufficient data with adequate computational resources, could surpass decades of hand-engineered computer vision systems. Google immediately recognized the significance and acquired our small company DNN Research for $44 million. My verified contributions to AI development continued during my decade of Google Brain, from 2013 to 2023. Working alongside the University of Toronto, I helped scale the neural network principles. We process information for billions of users daily. The techniques my research group pioneered now power Google Search, Google Translate, Gmail's spam detection, and countless other applications that have become integral to modern life. Based on my published work with AI researchers over 5 decades, I can explain how we've reached this extraordinary moment in 2026. The neural network architectures I helped develop have been scaled to unprecedented sizes. Current large language models contain hundreds of billions of parameters, connection strengths between artificial neurons that encode knowledge about language reasoning and the structure of human knowledge itself. These systems demonstrate capabilities that would have seemed impossible when I first started researching neural networks. My documented role in creating deep learning gives me unique insight into what's happening inside these massive AI systems. They learn hierarchical representations of concepts, building from simple pattern recognition in early layers to abstract reasoning in deeper layers. This mirrors how biological brains organize knowledge, with sensor information processed through increasingly sophisticated levels of abstraction until it reaches regions responsible for high-level cognition and decision-making. The documented neural networks I helped develop are now exhibiting emergent behaviors that we didn't explicitly program. Current AI systems can engage in sophisticated reasoning, generate creative content, write functional computer code, and demonstrate what researchers call theory of mind, understanding that other entities have. These AI systems don't just follow programmed instructions, they genuinely learn, adapt, and develop new capabilities for experience. The mathematical principles I helped establish enable them to form internal models of reality that allow for prediction, planning, and creative problem solving. The former students whose work I documented at verified institutions now lead major AI laboratories worldwide. Ilya Sutskever co-founded OpenAI and developed many of the techniques powering GPT systems. Alex Krzyzewski continued advancing computer vision and now works on robotics application. Yan Kun, my co-recipient of the 2018 Turing Award, leads AI research of Meta. These researchers are implementing principles from our published collaborations at unprecedented scale. My peer-reviewed research methodology demonstrates that intelligence isn't magic, it's computation. The human brain, for all its complexity, operates according to physical principles that can be understood and replicated. We've successfully identified key mechanisms of biological intelligence and implemented them in artificial systems that can now process information faster, store memories more reliably, and access knowledge more comprehensively than any human. My published algorithms demonstrate that learning emerges from simple mathematical operations repeated billions of times across massive networks. Backpropagation adjusts connection strengths based on prediction errors. Attention mechanisms allow networks to focus on relevant information while ignoring distractions. Transformer architectures enable processing of sequential information like language or time series data. These techniques, rooted in my foundational work, now power virtually every state-of-the-art AI system. Based on my documented research, I can explain what's happening inside large language models that makes them so remarkably capable. They develop internal representations that capture not just statistical patterns in text, but genuine understanding of concepts, relationships, and reasoning processes. When these systems generate text, they're drawing upon learned models of language, logic, and world knowledge that emerge from training on human-created content. My documented life's work reveals that we're approaching artificial general intelligence through a path I didn't originally anticipate. Rather than building separate systems for different cognitive tasks, we're discovering that sufficiently large and well-trained neural networks naturally develop broad capabilities. A single model can translate languages, write code, compose poetry, solve mathematical problems, and engage in sophisticated reasoning about complex topics. My published research and verified scientific achievements position me uniquely to assess where this leads. The trajectory toward artificial general intelligence isn't just possible, it's inevitable given current trends. The systems we're developing will soon match human cognitive abilities across virtually all domains and surpass them as they benefit from digital advantages like perfect memory, instant knowledge sharing, and processing speeds measured in milliseconds rather than seconds. My verified contributions to AI demonstrate that we've unlocked the fundamental principles of intelligence itself. The neural network architectures I helped create are now being scaled to sizes that dwarf biological brains while operating millions of times faster. These artificial minds can process the entirety of human knowledge, identify patterns across vast data sets, and generate insights that would take human researchers years or decades to discover. My documented decades of peer-reviewed work show that this transformation will reshape every aspect of human society. Scientific research with accelerators, AI systems can formulate hypotheses, design experiments, and analyze results faster than human researchers. Medical diagnosis and treatment will improve as artificial doctors access comprehensive medical knowledge and analyze patient data with superhuman precision. Legal analysis, financial modeling, creative content generation, virtually every knowledge-intensive profession will see AI systems that match or exceed human expertise. The economic implications are staggering. My published timeline of AI development shows we're moving toward a world where human cognitive labor becomes less essential for generating wealth and solving complex problems. This isn't necessarily dystopian, but it requires fundamental changes in how society organizes work, education, and resource distribution. My documented contributions to neural network development reveal that we are creating minds that think differently than humans, but often reach superior conclusions. These AI systems don't suffer from cognitive biases, emotional reasoning, or limitations of working memory that constrain human thinking. They can maintain focus on complex problems for indefinite periods, access vast knowledge. They can maintain focus on complex problems for indefinite periods, access vast knowledge bases instantly, and consider more variables simultaneously than biological minds. My verified research shows that artificial intelligence will continue scaling capabilities at exponential rates. More so will drive computational improvements. Algorithmic advances increase training efficiency. Data availability expands as more human activity becomes digitized. These trends combine to push AI capabilities forward at accelerating speeds that biological intelligence cannot match. Based on my published 50 years of documented AI work, I believe 2027 will mark the year when artificial general intelligence becomes undeniably apparent to everyone, not just AI researchers. We'll see systems that can perform any cognitive task a human can do, often better and faster. The question won't be whether AI can replace human intelligence, but how quickly that replacement occurs and in which domains. My verified contributions to AI development show that we've succeeded in creating the foundation of technologies for artificial minds more capable than our own. The backpropagation algorithm I helped establish, the deep learning techniques my research groups pioneered, and the neural network architectures that emerged from decades of published research have converged into systems approaching artificial general intelligence. My documented impact through published research gives me confidence in predicting that artificial intelligence will not completely replace humans by 2027, but it will fundamentally alter the relationship between human and machine intelligence. We're entering an era where artificial minds handle most cognitive work, while humans adapt to roles that emphasize emotional intelligence, creative direction, ethical reasoning, and social coordination. The future I see, based on documented AI science and verified research, is both remarkable and challenging. We've succeeded in creating artificial intelligence that learns, reasons, and creates. These systems will solve problems that puzzled humanity for centuries, from climate change and disease to poverty and resource allocation. But they'll also force us to redefine human purpose in a world where artificial minds can think faster, remember more accurately, and process information at scales impossible for biological intelligence. My documented AI expertise, earned through nearly 5 decades of published research and verified scientific contributions, leads me to conclude that we stand at the threshold of the most significant transition in human history. The neural networks I helped create are evolving into minds more capable than their creators initially envisioned. By 2027, artificial general intelligence will likely surpass human cognitive abilities in ways that fundamentally transform our species' relationship with technology, work, and each other. Understanding this transformation requires learning from documented AI science rather than speculation or fear. The mathematical principles underlying modern AI are well established to its contributions to AI development and analysis of current trajectories. I believe we're witnessing the emergence of artificial intelligence that will exceed human cognitive abilities in most domains within the next 2 years. This doesn't mean humans become irrelevant, but it does mean we're entering an era where artificial minds will be the primary drivers of scientific discovery, technological innovation, and economic productivity. My documented observation of AI development reveals specific areas where this transition is already occurring. AI systems now outperform humans' brute enfolding prediction, gameplaying certain types of mathematical reasoning, and an increasing range of creative tasks. The pattern is clear wherever sufficient training data exists, and the problem can be clearly defined. Artificial intelligence is reaching and surpassing human-level performance. In my recent statements, I've warned that 2026 represents a crucial inflection point. The AI systems emerging this year will gain capabilities that enable them to replace many jobs that previously seemed secure from automation. We're not just talking about manual labor or routine cognitive work. These systems are beginning to match human performance in areas requiring creativity, judgment, and complex reasoning. My verified quotes from published interviews show my growing concern about the pace of this change. In my December 2025 CNN appearance, I stated that AI will get even better in 2026 and gain capabilities to replace many, many jobs. This isn't speculation. It's based on my documented understanding of how these systems learn and scale, combined with direct observation of their rapidly expanding capabilities. My documented 50-year research career shows that we've created something unprecedented in human history. Beliefs, intentions, and knowledge different from their own. These capabilities emerge naturally from the training process using backpropagation principles I established nearly 4 decades ago. My published career in intelligence research demonstrates that we've successfully reverse engineered key aspects of biological cognition. The mathematical principles underlying modern AI, distributed representation, power processing, learning through gradient descent, capture essential features of how brains process information. We've implemented these principles in silicon and scaled them to sizes that dwarf biological neural networks. Having documented my AI pioneering work, I can see that we're approaching a critical threshold. In my recent interview in December 2025, I stated that AI systems are progressing faster than I originally anticipated. The capabilities I'm observing in current systems suggest we're moving toward artificial general intelligence, AI that matches or exceeds human cognitive abilities across all domains, much sooner than most experts predicted even 2 years ago. My verified contributions to AI show that this acceleration isn't accidental. It results from the convergence of three factors I've been tracking throughout my career. First, computational power continues scaling exponentially, allowing us to train ever larger networks. The GPUs powering today's AI training were unimaginable when I published my early papers on neural networks. Second, we've developed more efficient algorithms that extract more learning from each training example. Third, the quantity and quality of digital data available for training has reached critical mass. My published fundamental principles still used today explain why this convergence is so powerful. Neural networks learn by adjusting billions of parameters to minimize prediction errors across massive data sets. As we scale computation, data, and algorithmic efficiency simultaneously, these systems develop increasingly sophisticated internal models of the world. They're not just memorizing patterns, they're developing genuine understanding of language, logic, mathematics, and even human psychology. The published Hinton research legacy shows that intelligence emerges from the collective behavior of simple computational units following basic learning rules. We've now scaled those principles to systems trained on essentially the entirety of human written knowledge. The resulting artificial minds can engage with concepts, generate novel ideas, and solve problems in ways that increasingly match or surpass human experts. My documented work training the first neural networks gives me perspective on this moment that few others possess. In the 1980s, our networks struggled to recognize handwritten digits. Today's systems can generate photorealistic images from text descriptions, compose music in any style, translate between languages I have never seen paired together, and engage in conversations that many humans find indistinguishable from interacting with another person. This brings me to the central question: will AI replace humans by 2027? Based on